think, but please have a look if you're interested.
Take it away.
Hello everyone, and thanks for the organizers. So I'm Jean-Baptiste Delisle from Geneva University, and I will present S+LEAF, which is a fast Gaussian process framework for the joint analysis of radial velocities and activity indicators. So the framework is very similar to what Oscar just presented. So I will maybe go through my first few slides a bit more quickly because I presented the context.
Can you make the presentation full screen? It helps a bit. Yeah. Thank you.
So as Oscar explained, we model the stellar activity induced on the radial velocities through a Gaussian process, mainly because we don't have a simple model for activity. But we have some clues about what happens, what are the physical processes that are at stake, and their typical time scales. So this is a typical use case for Gaussian processes. So basically, the Gaussian process model, the Gaussian process framework we will use is to model the radial velocity time series with a deterministic part, which corresponds to the reflex motion due to the planets, and a Gaussian process part, which is here to model the stellar activity and some measurement error. So the Gaussian process time series itself, we don't know how it behaves exactly. So it's unknown even when we specify all the parameters of our model. We don't know what is exactly the time series of the Gaussian process, but we assume it to follow a Gaussian distribution, and with a given covariance, which depends on the kernel we choose for Gaussian process. So the Gaussian process is usually assumed to be stationary, which means that the kernel only depends on the time lag between two measurements. So the covariance only depends on the time lag between two measurements. So then if we also assume the measurement error to be Gaussian, at the end, our likelihood will also be a Gaussian, and the full covariance matrix of this Gaussian will be the sum of the Gaussian process parts given by the kernel and our measurement error covariance, which is typically assumed to be diagonal in case of white noise. So now, depending on the kernel we choose for the Gaussian process, depending on the hyperparameters of this kernel, we can have different behavior for the Gaussian process time series. And here I took this plot from the Celerité paper of Forman Maki et al. 2017, where we see different kernel functions and some realization of the Gaussian process time series for each kernel. So each time we have three different realizations that correspond to the exact same kernel. And we see that depending on the kernel, so for instance, the blue one is only a decay, and the red one is has some strong correlation here at a given period and strong anti-correlation at half the period. We see that the time series behave differently, and here we have something that is very similar to a sinusoid. But what is very important to notice here is that at a given time, we don't know at all what is the value of the Gaussian process. It's not encoded in the kernel we choose. So it could be positive, it could be negative, but what we know here is that if it is positive at this time, then a period later, it's very likely to be positive also. because we put a strong correlation at this period. And of course, if it's negative, there is a strong probability that it will also be negative. So this is what is encoded in the kernel we choose, the Gaussian process. So the problem here is that Gaussian processes are very flexible. It's a good thing when we want to model stellar activity because we don't know exactly how it behaves. So it's a good thing that it's flexible. But of course, it can absorb planets. So you can have some overfitting, especially because the signature of planets of stellar activity is very similar in radial velocities. In particular for spots which have a quasi-periodic signature in the radial velocities. So if we want our kernel to be able to model well this quasi-periodic signature of the spots, it will also model very well the planets. So that's where using activity indicators, as Oscar explained, is very useful because it can constrain our Gaussian process. So the family of model, the FF prime family of models proposed by Egrin in 2012 and later by Rushpole in 2015. So the idea here is to model with the same Gaussian process both the radial velocity time series and activity indicators time series. So the model of Rushpole et al. 2015 here is the following. So we model the radial velocities with a coefficient in front of the Gaussian process plus a coefficient in front of its derivative. And we do the same for the activity indicators with different coefficients. So as Oscar explained, this use of the derivative of the Gaussian process is both explained from a physical motivation, but also it allows to have some more flexibility in the model beyond just a linear correlation between the different indicators. So again, here, the Gaussian process G, we don't know the precise time series of it, but we assume a kernel for the Gaussian process and thus some correlation between the measurements. And because we use the same Gaussian process in all the time series, we will have some correlation between all our measurements. So the measurements of the radial velocity at a given time will have some correlation with the measurement of an indicator at another time. And we need to model the full covariance matrix of all the measurements. And in this covariance matrix, we will have terms coming from the correlation of the Gaussian process with itself, but also with its derivative and of the derivative with itself. So when we do this, as also Oscar showed, it's very efficient and very powerful to model the stellar activity. And here I just put an example on HD 13808, where we see the Gaussian process that is adjusted on the data and its derivative, and the combination of the two that is adjusted for the radial velocities and the indicators. And here it's just a zoom of the same plot, but on a specific time range, where we better see how it behaves. And we see that the time series of the Gaussian process for each indicator or radial velocity is slightly different because we have this coefficient in front of the Gaussian process and the coefficient in front of the derivative. So we can go beyond a simple linear detrending of the radial velocity by the indicators. But we have still some constraints from the indicators to model the radial velocities. Okay, so now we have seen that it's very interesting and powerful, this model, but the main issue is the computational cost of the Gaussian process. So since we have we assume a Gaussian process, the likelihood of the model will be a Gaussian distribution. And so if we use an MC-MC approach or nested sampling approach, we will need to evaluate many times the likelihood. And in this likelihood, what we need to compute is the determinants of the covariance matrix and basically the chi-square. So with the residuals of our deterministic model, and we need to solve this matrix problem. And in the end, the computing the likelihood, the cost of computing the likelihood will typically scale as the number of measurements cubed. And this can be a very
I don't know where this is coming from, I'm sorry.
Well, he's complaining about the computer, so the computer is complaining back.
I thought there isn't someone who's connected who's not muted, is there? Otherwise, I have to try and find out.
Put a message?
You just exit full screen and try to find out if it's... Oh, is it?
Mom is just talking you on his phone.
Someone joins the meeting then.
I see.
I can have a look.
It's a window and you solve it.
It's very, very slow.
Have you been thinking about it the whole time?
It bothers me. You could continue your presentation if you want. The presentation is visible through the Teams, but while Louise is trying to fix the problem.
I mean, we could turn the audio off on the computer, but we lose the online speed.
If you switch off the audio, they won't pick up what you're saying.
And if anyone online wants to say something.
Okay, good idea.
Yeah. I'm just gonna do a little. You
They can use the Slack channel.
Yeah.
It's okay? Yes. So I was saying that the cost of evaluating the likelihood scales as the number of measurements cubed. So if you have a lot of measurements, it starts to be very intensive in terms of computations. And typically, I think a few hundreds or a few thousands of measurements start to be very hard to deal with such a model. And of course, if you model the radial velocities plus 2 indicators, it means that you increase the number of measurements by a factor of 3. So in terms of cost, it multiplies by a factor of 27. So this model is very interesting, but very costly. Luckily, we have some ways to reduce the cost of evaluating the likelihood. And the most obvious one is if the covariance matrix is diagonal, then it's much simpler. Everything simplifies, and the cost is typically linear in terms of number of instruments.
But of course, assuming a diagonal covariance matrix, it means that you have white noise on no Gaussian process, so it's not very interesting. But more generally, if you have a sparse representation of the covariance matrix and dedicated algorithms that are specialized for this sparse representation, then you can compute those the determinants of this solving problem with a reduced cost. So this is the idea behind Celerite from Forman, Mackie et al. 2017. And in Celerite, they use a semi-separable representation of the covariance matrix. And basically, the main idea in Celerite is that the exponential of the sum is the product of exponentials. This is the main trick in Celerite, actually. So if you assume your kernel to be a simple exponential decay, you can split it in the negative exponential at time ti and the positive exponential at time tj, assuming that ti is bigger than tj, so assuming that you are in the lower triangular part of the covariance matrix. And when you do that, you can define a vector u that is the negative exponential, a vector v that is the positive exponential, and you can reconstruct the full covariance matrix just with the diagonal parts, and on the lower triangular part, just the product uv, and the upper triangular part, it's also the product vu. So the idea in Celerite is that you never work with the full covariance matrix, but you always work with those vectors. So you have three vectors, the diagonal u and v of size n. So it's a sparse representation of the covariance matrix, and you have dedicated algorithms that directly work with this representation to compute the likelihood. And so you have a linear cost of evaluating the likelihood. So of course, in Celerite, you can do a bit more than just an exponential decay, because you can combine different terms with exponential decays on sine and cosine. And then you don't have just vectors u and v, but you have matrices with several columns. And the number of columns in u and v is called the rank of the representation. So in this case, we have just vectors, so it's a rank 1, we have just one column. But of course, if you have more, a higher rank, it starts to be a bit more costly to evaluate it. So the evaluating the likelihood, the cost scales as the rank squared times the number of measurements. So it means that as long as your rank of the semi-separable representation is lower than the number of measurements, it's interesting to use this. So even if your rank is 10, if you have 1,000 measurements, it's very interesting to have this representation. So now, if we want to apply Celerite to the problem of radial velocities plus indicators, we have two main problems to solve. First, we need to apply it to several time series at the same time. And the second issue is that in Celerite, there is no modeling of the derivative of the Gaussian process. So we need to account for the fact that we have in the model both the Gaussian process itself and its derivative. The first problem, so having several time series, has been actually solved by Gordon et al. 2020. So 3 minutes. In the model, so it's very similar to what we want here, but there is no derivative. So we have several time series with a deterministic model, so the planets or the offsets, and a coefficient in front of the Gaussian process, different coefficient for different time series. And they assume also the same calendar for all the time series, but actually this assumption can be relaxed. And in order to be able to apply celerity, the trick is simply to define merge time series with all the different time series, so the radial velocities and the indicators, in the same vector, and you sort them by increasing time. So you have, for instance, the first RV measurements, then the first bisector measurements, the first HK measurement, and then all the second measurements, etc. And then you simply define new U and V matrices, which are simply the coefficient alpha that is here in front of the UV representation of the Gaussian process kernel. And with this, you can directly apply celerity, and the cost is linear in terms of the total number of measurements. So if you have k time series with n measurements each, the cost will be linear in terms of kn. So as I said, you can relax also the assumption that all the time series share the same calendar, so you can actually mix different time series coming from different instruments and still apply this. So now we need to include the derivative of the GP in the model, which means that, as I said, you need to compute the covariance between the Gaussian process and its derivative and the covariance between the derivative itself. And if we come back to the semi-separable representation of the GP, so our kernel is separated in U, V part, where U only depends on Ti and V only depends on Tj. So when we want to compute the covariance between the derivative and the Gaussian process, we simply need to derive the kernel with respect to Ti. So we only need to compute the derivative of U times V. And here we only need to compute U times V prime. And for the covariance of the derivatives, we need to derive both U and V. So actually, to apply celerity to this problem with the derivative, we simply need to compute the derivative of U and V, so semi-separable decomposition of the covariance matrix. And what is very nice is that then we can constrict our vectors U and V for the full covariance matrix by taking alpha, so the coefficient in front of the Gaussian process times the GPU, plus beta times the derivative, and for V the same. And we have only for each term in the original Gaussian process, we have only one term in the final representation of our covariance matrix, which means that basically the derivative here comes from free. We don't increase the rank of the representation by including the derivative in the model. And if it was not possible to have this factorization here, we would have 4 different terms, because here we have 4 different terms. And 4 different terms mean that the rank would be multiplied by 4 and the cost by 16. So it's very nice to have this factorization that happened here. Okay, how long?
Minus 3 minutes.
Okay, so I will.
You were supposed to body check him, weren't you?
Yeah.
Maybe quickly this because so the difficult part then, the only missing part is to select a proper kernel to apply this. because of course we cannot do any kernel with semi-separable representation, but we can play with the kernels that are available in Celerite to try to mimic the kernel we want. So we can combine as many Celerite terms as we want. Of course, if we have lots, it will cost more. But we can try to mimic here a squared exponential kernel. Only it works quite nicely. And here, so the what I call the SEP kernel is the quasi-periodic kernel that Oscar was showing earlier, with the exponential of a sign inside it. And we can, in this case here, with the, I think you called it a low harmonic complexity. Yeah, so here it's easy to reproduce it with Celerite kernel. Of course, with high harmonics complexity, it's more and more difficult, and you would need lots of Celerite terms to do this. And yeah, just maybe the performances. Oh. I guess
That's it, it's showing.
just the performances to show the improvements. So here it's the full using the full covariance matrix, and here it's with the Celerite kind of approach. And we typically for the case I showed, we have like 700 measurements, and we have an improvement of 2 orders of magnitude to compute the likelihood. And of course, for more measurements, it's efficient. Okay, I'll stop there.
Cool. Thank you very much. Now we have time for one question, and if our next speaker could start can share their slides as well.
Our next speaker's online.
Okay, cool. We can't hear them.
Yes.
That's all right.
I'm going to do that while you do it.
Okay, thanks, Sam. But while Sam sets up, if we have questions, a quick question. Elise, I see your hand.
Thank you. I was wondering, you said that the similar calendars were not necessary per se. I was wondering, how flexible are you in that? Like, how far off can you go in calendars before the whole thing starts breaking down?
So it's the same as the issue will be the same as for a classical approach for Gaussian process with the full covariance matrix. The idea is that if your data sets are completely apart, then you have no information to share between the data sets, because the correlation is very weak between your two data sets, so you don't learn anything by combining it, and you just lose time by combining it. But then, so yeah, it depends also on the kernel, on the decay of your kernel, of course, because if your decay is very rapid, then even if you have very close data sets, you don't have any correlation, and it's independent, basically.
Can I? No? Yes.
Yeah, quickly.
We'll talk.
Quickly. Yeah, no, talk offline. Yeah. Online in the chat so that everyone can participate. Yeah. Thank you very much. Let's thank our speaker again.